Okay, so recording has begun. So welcome to today's EnviroSchool professional learning session. We are once again excited to share with you some of the expertise of our staff here at EGLE. So today's session is titled Radioactive Michigan, and it's focused on some really cool parts of our work around radiological materials in Michigan, protection, and what you can do to protect your health. The EnviroSchool Educators Series, for those of you who are joining us for the first time, is a new venture out of EGLE Classroom. We developed this resource in order to provide resources to educators in the state as they teach others about Michigan's environment. We wanted to help build connections between educators and environmental professionals in the field that can give them information and resources on those topics. And we wanted to help advance our mission of protecting the environment and public health through environmental education. So we are offering sketch credit for those of you who are K-12 educators. So stay tuned. Once we get to the Q&A portion, I will drop an exit ticket in the chat for you to complete. You'll need to complete that in order to receive the 1.5 credits for participating live in the webinar. So just a little bit about EGLE, for those of you who are new to us. We are the Department of Environment, Great Lakes, and Energy, previously known as DEQ, if that's more familiar to you. Our mission is to protect the environment and public health of Michigan through the management of air, water, land, and energy resources. We do a lot of different things. We enforce state and federal rules that are designed to protect our natural resources and its people. This includes things like limiting pollutants, inspecting facilities, enforcing regulations, investigating spills and emergencies, doing a lot of air, land, and water quality monitoring. And then there are a lot of us who work sort of behind the scenes doing outreach, technical assistance, and financial assistance to make sure that all these programs happen. You don't need to memorize our whole org chart, but what I want to show you is that we have some primary program divisions that cover these major topics of air, land, water, waste, pollution cleanup, and so on. So our primary program divisions, where our staff are coming from to give these presentations to you, are the air quality division, the water resources, drinking water and environmental health, materials management, remediation and redevelopment, and oil, gas, and minerals division. So some of our past EGLE Classroom EnviroSchool webinars have focused on water resources, drinking water, oil, gas, and minerals. And then our last webinar and some of the upcoming ones, including today, are focusing on some different parts of our materials management division. So just to give you a sense of where we're coming from as a department and where we're coming from with our professionals giving these presentations to you. So today you're going to hear from 4 of EGLE's staff from Materials Management Division who work in a really interesting area with radiological materials and radiological protection. And if you gentlemen would like to turn your cameras on, now would be a great time. Our presenters today are T.R. Wentworth. He's the manager of EGLE's Radiological Protection Section. Jay Paquette, the supervisor for EGLE's Radioactive Materials Unit, and Les Smith, who is Michigan's Indoor Radon Program Coordinator. And with that, I'm going to turn it over to them to be the experts guiding you through all the cool things that have to do with radioactivity and radiological materials in Michigan.
Okay, thanks, Eileen. As Eileen mentioned, my name is T.R. Wentworth. I'm the manager of the Radiological Protection Section. Okay, thank you. A little bit about, first I'd like to just describe what our section, how our section is constructed, and a little bit about what we do before I talk about radioactive material and radiation generally. So Eileen showed the org chart for the department, and she mentioned that one of the divisions that she's been dealing with is materials management. So you see our org chart there. We're in materials management. And you see us near the bottom there, radiological protection section. So within the section, we've got 2 units that perform our mission. Our mission is to control, is to prevent unnecessary exposure to ionizing radiation. So to do that, we've got 2 units for that purpose. We've got our radiological emergency preparedness unit, And we've got our radioactive materials unit you see down there. You also see displayed there a low-level radioactive waste authority. That's not actually a staffed authority right now, but we do provide some functions related to that authority. Next slide, Eileen, please. So within the two units, the Radiological Emergency Preparedness Unit is responsible for planning, including field radiation monitoring and sampling collection for an event near a nuclear power station. We do a lot of calibration and equipment maintenance relative to this task. This program is required by FEMA for all states with nuclear power stations. All states are required to have response capability in the event of an accident. And so part of that is FEMA evaluates our response to those scenarios on an annual basis. Within our materials unit, is broken up into three different parts. We have our state indoor radon program. And Les is going to go into more detail on that later on, but the radon program is funded in large part by an EPA grant. It's an outreach program where we encourage Michigan residents to test for radon and mitigate if they have radon levels above 4 picocuries per liter in their living zone. So we primarily provide outreach materials to county health departments, tribal government, and some other outreach program partners. Another program in the materials unit is our radioactive materials program. That program is responsible for registering and inspecting companies involved in the cleanup of naturally occurring radioactive material. This is a material that is associated with certain industrial operations. They also respond to notifications of radioactive material found at scrapyards, landfills, other unexpected places. And we get notified frequently by scrapyards and landfills who, in most cases, have radiation detection equipment at their scale. We also do quite a bit of public outreach. We take questions from the public frequently, and we've assisted citizens over the years with handling radioactive material that they might have found and been surprised by finding. The last program that we have in the unit or in the section here is our Radiological Protection Laboratory. The laboratory is primarily responsible for testing environmental levels of radioactivity around the nuclear power stations in the state. The samples include, they do surface water, air, ambient radiation, as well as milk sampling in the vicinity of the power stations. That program was begun in 1958, prior to any nuclear power stations operating in the state to establish a baseline. That's been ongoing ever since then. Next slide, please. So in addition to what we do, there are several other regulatory bodies that operate within Michigan, and I'd just like to point these out. At the state level, there is a program called the Radiation Safety Section in the Department of Labor and Economic Opportunity. They keep changing their department on me. And they are responsible for inspecting and regulating machine-produced ionizing radiation. And when you think of machine-produced ionizing radiation, that's primarily X-ray units. It could be accelerators. And there are a host of other sort of less common uses of machine-produced radiation. Also within Michigan, the US NRC licenses and inspects most uses of radioactive material in the state. And these would include nuclear medicine, nuclear power, industrial uses, and other uses. The US EPA sets radiological standards also within the state. One of the primary standards that you may be familiar with the EPA is their setting of the radionuclide limits allowed in municipal water supplies. So municipal water supplies are required to clean up any any radioactive material in the source water to a certain limit, and they established that. And lastly, the U.S. Food and Drug Administration has a device program which is responsible for licensing and approving the design of all radiation-producing machines that are sold or imported into the United States. Next slide, please. So I'll just like to go ahead and start talking about radioactive material, just generally. So maybe you all have heard of this before, but it's generally recognized that Wilhelm Röntgen was sort of given credit to first discover ionizing radiation, and he discovered X-rays in the year 1895. Shortly after that, Henri Becquerel discovered radioactivity in uranium ores. He noticed that uranium ores were darkening film, and they were apparently emanating some kind of mysterious rays. And then shortly after that, the Curies, Marie and Pierre, chemically separated radium in 1898. Becquerel and the Curies worked pretty closely together during this time period. So there's a fair amount of overlap between their work. Next slide. Okay, so the next slide here, just want to point out, so when we talk about radiation, we distinguish between ionizing and non-ionizing sources of radiation. So what's depicted here, of course, is the electromagnetic spectrum. You'll see long wavelength, less energetic electromagnetic radiation when you're down in the radio wave range, up into microwaves and infrared. The kind of radiation that we deal with and that we're going to be talking about for the rest of this presentation here is called ionizing radiation. These are photons that are energetic enough to take an electron out of an atom or a molecule. And you can see there on the slide there, at the top of the slide, excuse me, sort of puts the difference between ionizing radiation and non-ionizing radiation. And we generally deal with, starting at X-rays and going up in energy with shorter and shorter wavelengths. Next slide. Other types of ionizing radiation besides photons include alpha radiation. This is the most energetic form of radiation. It consists of 2 neutrons and 2 protons, or an ionized helium nucleus. It's the most energetic. It's also the most easy to shield from. The other type of radiation is beta radiation, which is a high-speed electron or positron. Gamma rays and X-rays are both photons, but they're distinguished by the fact that gamma rays originate from within the nucleus. X-rays are produced in the electron cloud that surrounds the nucleus, but frequently with radioactive decay, there will also be X-rays emitted as a result of the atom settling to a ground state following a nuclear decay. Neutrons are listed here also. They're not commonly encountered. There are a number of applications where neutrons would be present, but they are ionizing radiation. Next slide. So I'm showing the periodic table here to just have a discussion about elements. In a periodic table, the element in each row increases from left to right, with the right-hand column being the noble gases or a closed electron shell. So the periodic table distinguishes between how different elements behave chemically. They predict how elements will behave chemically. But what I want to talk about is isotopes, because that's where we start getting into radioactivity. So next slide, please. So within a given element, you can have different isotopes of different weights. An isotope means 2 or more forms of the same element that have the same number of protons, but differ in the number of neutrons in their nuclei. So For example, I listed here that there are 3 isotopes of lead there. They all have the same number of protons, but they have a different number of neutrons. Those particular isotopes are all stable. Another example is carbon-12, which is the most common isotope of carbon. Usually when you think of carbon, you think 12, at least I do. But carbon-14 is a commonly produced radioactive isotope of carbon. It's constantly being produced in the upper atmosphere, and it rains down and is uptaken into the biosphere by animals, the eating plants that have radioactive carbon. And this is the principle that's used in radiocarbon dating, for example. Next slide. So here's another kind of chart. This is called the chart of nuclides. And I know that's pretty difficult to see on this scale. Typically, the chart of the nuclides is depicted on like a wall length chart, a nice log poster. But I put it here just to demonstrate a few things to you. So first, what you should notice is that the proton number on the x-axis increases as you go left to right. I'm sorry, as you go on the y-axis from bottom to top. And the neutron number increases as you go left to right. A couple of things to note about this graph is the z equals n line there. That shows where the number of protons would be equal to the number of neutrons. And you can see how it meanders away from that line as you go up in atomic number as you get into larger and larger nuclei. The dark region that runs down through the middle of that, those are basically the stable isotopes that run through the middle of that region there. Next slide. And so here is a detail of that chart at the origin, okay? So you can actually see what's going on here. So if you look in each row, those are all the same elements. So for example, hydrogen, left to right, those are all different isotopes of hydrogen. And as you move up, you'll see carbon is the highest element in this detail that I've cut out. You'll see on this particular chart, the blue squares represent stable isotopes, and the numbers in those blue squares give the natural abundance for that particular isotope. So you'll see carbon-12 and 13, for example, both exist in nature, but roughly 99% is carbon-12. You'll see also carbon-14 there depicted to the right. And that's got a half-life of 5,700 years. Again, harking back to what I was saying, that's the principle used for radiocarbon dating. You'll also notice at the very bottom in the origin there, the N, that stands for neutron. So a neutron outside of the nucleus has a 10-minute half-life, 10.25-minute half-life. So like I said, it's not commonly encountered, but neutrons do exist and they are ionizing radiation, and they're shown on the chart here. So next. Okay, now this slide depicts a radioactive decay chain. So in nature, there's actually quite a few of these natural radioactive decay chains. The one shown here is got uranium-238 at the head of the chain. This is called the uranium-238 chain. And it's interesting because, well, notice a couple of things. The atomic number is listed along the top there. So, and each transition is depicted by a certain type of radioactive decay. So for example, when you go from U-238 to thorium-234 by alpha decay, you see that the atomic number drops by 2. That's because the 2 protons that were in that alpha particle were transmitted out with the radiation. So that's how the atomic number changes as radioactive decay takes place. A couple other things to notice about this is the number of different lead isotopes. Well, actually of several different isotopes. So if you go on the left there, you'll see lead-214, lead-210, and lead-206. Those are all different isotopes of lead. lead-214 and 210 are both radioactive, so they're still in the decay chain. And eventually this decays down to a stable lead-206. Next slide. So the last slide that I'm going to present here, just a couple of demonstrations or a couple of pictures of different kind of measuring instruments. One of the well, ionization chambers or ionization detectors are gas-filled chambers. That's one of the oldest type of detectors that we use. And basically, you have a volume of gas, and when the gas is ionized by a field of radiation, that event is detected by the electronics in the unit, and that's how we detect the radiation that way. The other detector down there is a scintillation meter. That's a benchtop version. The probe, the black probe at the end of the cable there is where the detector is located. Scintillation detectors consist of a crystal that glows or scintillates. That's why they're called scintillation detectors. It scintillates when it absorbs radiation. The number of photons produced in the scintillation detector is proportional to the energy of the primary gamma or X-ray photon. And this is actually a nice property that can be utilized because if you know the energy of the primary photon, you can use it to fingerprint what type of radioactive isotope you're dealing with. The last detector type I put on there is film because believe it or not, there are still film dosimeters used in some industries. It's not very common. There are many superior dosimetry types, but film is still used occasionally to measure occupational exposures to radiation in like X-ray departments and so forth. That is what I have for my portion of this presentation. I'll hand it off to Jay now.
Thanks, TR. So TR explained a little bit of what radiation is and how we detect it, and the things we might be looking for. And so it's important to understand the units that we might utilize in doing our work. So as TR mentioned, in the early stages of discovering radiation, a lot of that was attributed to Curie, Marie Curie, and so we have a unit named after the Curies, and that is represented by 3.1 times 10 to the 10 decays per second. Interestingly enough, that comes from the amount of radioactivity that's emitted from 1 gram of freshly separated radium-226. The becquerel is maybe a more easy unit to understand. It's just simply 1 decay per second. That then is utilized to measure units of exposure, which is a Röntgen, which is still the most common unit we probably use today in the United States, but that is a measure in ionizing radiation made in air. And so that's what TR described in the previous slide a little bit with the ionization chamber. The second or the next unit down is what we refer to as absorbed dose. The gray and rad are units of absorbed dose, and that's a measure of energy that's going to be imparted to a material in the effort of stopping that radiation. And then lastly, we have what's called dose equivalent or biological dose, which is REM and sieverts. That takes into effect the absorbed dose and then quality factor having to do with what that dose is being exposed to and type of tissue, for instance, and any other modification factors. Those are multiplied together to give you a REM and sievert to give you a biological exposure risk. In general, in our industry, we typically say 1 Röntgen is equal to 1 rad is equal to 1 REM. It's just an easy generalization. So we'll take a lot of those units on the left-hand side, couple them with prefixes to make things a little easier for us. So often when we're talking about becquerels, because 1 decay per second would be a large number, we usually couple that with giga or megabecquerels, or curies will often couple with millicuries or microcuries. So those are just common prefixes we'll use, at least in our industry. On top of that, we'll couple them with rates or concentrations. So examples of those, which you'll see later on, are going to be concentrations of radon in air. So again, picocuries per liter is going to be an amount of radioactivity in a given volume of air. Same with radium in soil or any other material we're going to measure in picocuries per gram, whereas a survey of exposure, we're going to measure in milliröntgen per hour or perhaps Röntgen per hour in a very high radiation area. I put the trefoils over to in the middle of the slide there just to kind of give folks an idea of the symbol we use to label radioactive materials or radiation areas. Many people have seen those, maybe the signs associated with fallout shelters that are even still around in the area that are from the Cold War era. Next slide, if you don't mind, Eileen. So with those units, we measure radioactivity, right? But over time, what happens is this amount of radioactivity is cut in half. And so the way we describe this amount of time for a given material is referred to as half-life. And so there are two common equations that we use. I've listed those there. Won't go into those in detail other than that the A sub naught just simply refers to an amount of radioactivity, whether it's Curies or Becquerel at a beginning time, will be a subsequent amount of activity at a later time. So if you look at the bottom of the slide for fluorine 18, which has a half-life of 109 minutes, it's a common radionuclide used in medical procedure. For every 109 minutes, the amount of radioactive material is cut in half. It's important to note that this doesn't instantaneously occur at 109 minutes, but it's a continuous decay through that period at which, if you take a timestamp at 109, you expect to have 1.5 millicuries after the first half-life, and another subsequent half-life you'll have 0.75. It's interesting to note that the range in radioactive half-lives is from yoctoseconds, which is a prefix we don't usually use, to 10 to the 24 or 10 to the 30 seconds or 10 to the 24 years, which is essentially stable. It's mostly impractical for us to measure, but there are tons of radionuclides in a practical range like the one shown below. So if next slide, if many of you may know or may not know that there's a lot of use for radioactive materials in our everyday life. It's come and gone since its discovery in different types of uses, but some of them are depicted here on the slide. Everywhere from nuclear class submarines to common medical procedures like CTs, mammograms, standard x-rays. We use them in industry. The one in the middle is actually an x-ray tube for materials research. It is also natural in your food. Bananas, as well as milk, will contain a natural amount of potassium-40. The silver boxes that say Spec 150 are industrial gamma cameras. They're actually taken out into the field where it's impractical to take electrically powered x-ray tubes, and they will put x-ray film on the opposite side of a pipe, a weldment, and they will expose that pipe to the radioactive source in that gamma camera to take an image of a weld to ensure that the integrity of the weld is appropriate before putting fluids or gases through that pipeline. Of course, we do have incident radioactivity, which you'll hear about a little more later, which is radon. It's in welding rods, smoke detectors in our home, and sometimes we'll still see it in tritium exit signs, which will glow at night without the need for power. It's also important to note that despite radiation being present in our everyday life, its benefit can outweigh its potential risk. One example would be like using gasoline, which can be hazardous to us, but we use it in many of our everyday commutes to work, but that potential risk and the designing and safe practices outweighs the alternative modes of transportation. Eileen, if you could click the link at the bottom, this might be interesting for some of you to explore at a later time. Shortly after the discovery of radium and in subsequent decades into the 1920s, 30s, uranium was largely used as well as other radioactive substances in a lot of consumer goods. And so this is an interesting little snapshot of history with a lot of interesting consumer products. Actually, there's a whole little title there of consumer products, from things like uranium glazed pottery to some science kits for for home, some interesting old signage, and then again a lot of radium related products like table salt, soaps, butter, you name it. Radium was thought to be this very, very beneficial element when it was found. Yeah, and there are actually, I mean, thanks, this is a good point. There are a number of people that are avid collectors of a lot of these types of materials, and much of it is completely safe to own when handled properly. So you'll find that a lot of people will collect radium watch dials, uranium glass or other potteries and things like that, radium revigorators. So this is an interesting site to explore when you have time. One additional thing that you may find on that site is that a lot of schools historically had radioactive science kits. The image on the right is a civil defense unit that would have been issued from the government. A lot of municipalities and government agencies would have had these in the event of a nuclear fallout. Many of these kits were distributed to schools, and they would have had radioactive material included in them. Same with the image on the left, which is like an at-home cloud chamber. And again, that would have come with a radioactive source. Some schools also have called over the years with discovery of uranium ores and other such elements and materials that have been labeled. But when in doubt, if you've got a question about what to do with the material, its appropriate disposal or handling, don't hesitate to call us. We actually have a source recovery program where we can take licensable or controlled sources, we can take them back into the ownership of the state, and we have a program to properly dispose of those with waste brokers. So now, if next slide, Eileen. Now that we have some idea of the various locations of where radiation can be found, it's interesting to then look at where does our cumulative dose come from? What is it that's gonna perhaps contribute to our lifelong risk of perhaps getting cancer? So this is just an interesting slide to depict the different amounts of radiation you might expect to receive from a given medical procedure or as an exposure as part of your background. On the left-hand slide in the green area, on the right-hand side of the green area, you'll see that the largest contributor to your radon or to your radiation dose is actually radon. In general, that's coming from radon in your home. You'll see that that's also on the right-hand image. It's the second to top, although it's still well below 250 millirem per year. It's similar to getting a mammogram procedure. You'll note too, it's also, I think, an interesting thing to look at that living near a nuclear power station does not significantly contribute to your radiation dose. If you're interested in what your radiation dose might be, or students would be interested in doing it, there's an EPA dose calculator link. If you could bring that up, Eileen, there's an interesting way that you can kind of put together the amount of increased risk you may have. And there are a lot of contributing factors, although they're not terribly complicated, but some of them have to do with where you live, the elevation in which you live. The higher you are, the more exposure you're going to get from cosmic radiation. Internal radiation having to do with, believe it or not, whether or not you actually have fake teeth, and some travel-related items, how many miles you fly per year. Again, same thing. The higher you are in altitude, the more exposure you may have. So, for instance, flight attendants have a higher occupational exposure than most people do. And then there's a couple other items about smoking, which can increase your risk of radiation exposure. Same with luminous wristwatches. Keep in mind, not all luminous wristwatches are radioactive. We're talking about the old ones with radium. So students and you as educators can go through this and get an idea of what your total cumulative dose is. And the last one is interesting because it'll ask to put a concentration of radon in your home, and that's important to understand, and Les will talk about that a little bit more later. So now that we understand a little bit of where it comes from, how it contributes, how can we then prevent it? And there are three principles we use in what's called the practices of radiation protection principles, which are LARA, as low as reasonably achievable. The important thing to understand is there's a reasonable aspect to this. Not zero dose is not always achievable, so we keep the reasonable portion in there for that reason. The first one is time. The less, if you spend less time with the radiation, of course, you get less dose. It's cumulative as a unit per hour or per second dose rate. You can increase your distance. Radiation is, it decreases with distance as the 1/r squared as a point source. Or lastly, you can do put some shielding, put something between yourself and the source. So again, time distance shielding is what we utilize for ALARA. And then just to touch on this a little bit, there's a huge range of career opportunities in radiation or radiation fields, or fields that even touch in radiation, but they range in military. We work with the civil support teams. We started to meet with them. State of Michigan has one out of Battle Creek area. They do CBRN, which is chemical, biological, radiological response. But there's also tons in industry, X-ray techs, certified nuclear med techs. I mean, you name it. There's tons there in the medical field, but also nuclear power, materials research, et cetera. And then the standard scientists, technicians, and applications research that may come in schools. And of course, like folks, there are folks like ourselves that are doing regulation of radioactive materials, research in the government with the DOE, for instance, tons of scientists and technicians, and then of course emergency response personnel. In all of these careers, there's a huge variety of education experience needs, all the way from high school to PhD, and there's opportunity to go specialist trainings in schools that don't require bachelors, and some will require PhDs, of course. So that said, I'll pass it over to one of our specialists, and that's our radon specialist, Les Smith.
Thank you, Jay, and thank you, TR. Good evening, everyone. My name is Les Smith. I'm the State of Michigan's Indoor Radon Specialist. It's my pleasure to be with you in this EGLE Classroom session. Looking at our slide here, yes, this is January and it is National Radon Action Month. It's a very busy time around the state of Michigan and nationally out doing education outreach, informing our residents about the importance of testing for radon gas in their homes. And so we're going to talk about a little bit here in the coming slides, kind of pulling together some of the topics that both TR and Jay have already discussed about radiation. The things we're going to talk about is we're going to talk about what radon is. We're going to talk about what it does to us. We're going to talk about how it gets into our homes and any other building for that matter. We're going to talk about how to measure for radon, and we're going to touch a little bit about how to fix it. But before we get into the deep dive, we're going to do a 30-second public service announcement about radon.
1 in 4 Michigan homes has high levels of radon, a naturally occurring radioactive gas known to cause lung cancer. It doesn't matter where you live or what type of home you have. You won't even know it's there unless you test. So don't wait. Testing is cheap and easy. And if there's a problem, it's simple to fix. Visit michigan.gov/radon to learn more.
We took action. Will you?
All right.
What
is radon? Yeah, no worries. What is radon? So it's from our 30-second public service announcement. Radon is a naturally occurring radioactive gas. It originates in the rock and the soil underneath our homes. It originates in the uranium found all over the planet, here in Michigan and elsewhere. Some of the soil types or rock types that can contain uranium, including volcanic rock, granites, dark shales, sedimentary rocks. Sedimentary rocks containing phosphates and metamorphic rocks can all have some amount of uranium in it, which is actually the beginning of the decay chain, which ultimately leads to radon. Again, it's naturally occurring. It's no one's fault that it's there. It's just naturally part of the environment. Radon in the soil beneath homes and buildings enters from beneath the home where the home is in contact with the direct contact with soil, either beneath or on the sides. And I'll talk about that a little bit more in the coming slides. But one other thing I want to leave you with is that In all 83 Michigan counties, there have been radon levels found in all 83 counties, radon levels that have been found above the EPA's action level. And we'll talk about that in upcoming slides. Before we get into that, we'll talk about a little bit of what does, in the next slide, let's do some radon fast facts. I'm going to refer back to one of the slides that TR showed earlier. Where is radon? Radon does appear on the periodic table. It is as a noble gas. It is in the group 18 column in the periodic table. It has an atomic number of 86, mass number of 222. It is heavier than air. Just want to point those things out, that it is part of the environment. Radon and the decay products that I'm going to be talking about on the next slide are all found in the periodic table of elements. So on the next slide, we'll give you a closer look at what the radon decay products look like. It's, again, everything starts with uranium. Uranium, radium, and this is not the complete decay chain. The slides that both TR and Jay showed earlier, it's a much longer chain, but this is a kind of abbreviated look at what's in the decay chain. Again, starts with uranium, radium, what ultimately leads to radon gas itself. Radon gas, it has a half-life of 3.8 days, and it continues to decay until radon decay products, which you'll see here on the screen, 2 poloniums, bismuth, lead, another lead. Again, this is not the entire decay chain, but these are the ones that we commonly talk about in our radon circles. The 2 poloniums here are highlighted, and we'll discuss a little bit more on the coming slides, are of the most concern. These radon decay products are very small particles. They're radioactive. They all give off an alpha, which we've discussed in the previous slides. These are easily inhaled, and they have the potential to damage sensitive lung tissue. So on the next slide, we're going to explore more the health risks associated with radon decay products. So, sorry, next slide, Eileen, sorry. So atomic particles, like I mentioned, the radon decay products, when they break down, they're small, they're heavy metals, they're easily inhaled. Those are continuing to give off alpha energy, which can damage DNA. They can scar the lungs. They can kill lung cells. The lungs will, the body will try to recover from that, heal damaged lung cells. Sometimes over the course of a long prolonged exposure can lead to the development of lung cancer, and that's from the being exposed to a long-term. It's a long-term exposure, not a short-term. Again, these are no man-made sources of radon. They are all naturally occurring. So next slide, Elaine. Exposure to radon is a lifetime exposure risk. It is considered to be the leading environmental cause of cancer mortality in the United States. The United States Environmental Protection Agency estimates that radon-induced lung cancers lead to over 20,000 deaths annually in the United States. Again, because radon is odorless, colorless, and tasteless, you don't know how much you're being exposed to until you test the building that you're in or where you're living to find out what the radon levels are in that building. Next slide, thank you. Every home, this is one of the things I see in the radon office, and my colleagues across the country experience this as well, that there's a belief that radon is only in certain homes. Radon is in all homes, so every home has some measurable level of radon because all homes are in contact with the soil. There is no such thing as a safe level. That is a frequent question that is asked. There is some risk with radon exposure and its decay products at any exposure rate, and I'll talk about that here in the next slide. Many homes that have elevated radon levels can have the radon levels reduced to under 2 picocuries per liter. The US EPA recommends fixing a home when the home has been determined through testing to have radon levels at or above 4 picocuries per liter. And Jay touched on those units of measure previously. That is the action level for fixing a home. Next slide. So I mentioned that there was no safe number. The US EPA action level of 4 picocuries per liter for seven people in 1,000 are projected to still develop lung cancer at 4 picocuries per liter for non-smokers. That number increases significantly if it's a smoker. So 62 in 1,000 have an increased risk of developing lung cancer at 4 picocuries, which is the action level. As I mentioned, there's still some risk, albeit smaller, there's still some risk. There is still a greater risk for smokers at any category. The 2 picocuries per liter is the level at which you hope to get the levels in a home down to at a lower level. It's either the lower is the better when dealing with radon in a home. The 1.3 picocuries per liter is the average indoor radon level in homes across the United States. Smoking and other particulate exposure in a high radon environment poses an increased risk, as what the chart is showing there. According to the Center for Disease Control, people who smoke and are exposed to radon have a 10-time greater risk of developing lung cancer than those who have not smoked. So it's important both for smokers and non-smokers to find out the radon levels in their homes and to take steps to lower their exposure. So on the next slide, we'll talk about, well, how long have we known about radon? We've known about radon for a very long time. It goes back to the early 1900s when Friedrich Dorn first discovered it. Moving into the 1920s and 1930s, radon was suspected to be the cause of lung cancers, particularly for underground miners back in the 20s and 30s. Moving upwards into the 1950s, the focus turned to the radon decay products that I mentioned earlier. Those small particles in the decay chain were identified as the causative agent for developing lung cancers. And then 1984 came. 1984, the gentleman in the picture is Mr. Stanley Watrous. He was a nuclear power plant, a construction engineer for the Limerick nuclear power plant in Pennsylvania. Mr. Watrous one day, I guess, had been setting off the radiation detecting equipment at the power plant. Now, the power plant had not yet received its nuclear fuel for processing yet, because as the plant was still under construction. But somehow, Mr. Watrous was, in his comings and goings, was setting off the alarms. Through evaluation, they knew that he was not exposed to radiation at his job site because there was no nuclear fuel at the plant. But after going to his home and doing some testing of his home, they determined that his home had radon levels in excess of 2,700 picocuries per liter. That is several times above the EPA action level of 4 picocuries. The source of the radiation turned out to be radon and its decay products. The level of radon in the home was estimated to be the equivalent of smoking a couple of hundred packs of cigarettes per day. Mr. Watrous' experience raised the national level of attention to radon in homes at that time, and ultimately led to the creation of the Michigan Indoor Radon Program in June 1989. Mr. Watrous is currently, if anyone's interested, because looking at that's a really high number, Mr. Watrous is currently a certified radon mitigation contractor in the state of Pennsylvania and is currently still practicing radon outreach and mitigation. So next slide, we're going to talk about how radon gets into our homes, or any building for that matter. Next slide. Thank you. So how radon enters a home is going to depend on a number of things. It's going to depend on the strength of the radon in the soil. It's going to depend on how loose or tight those soils are. It's going to depend on the building to soil pressure difference. It's going to depend on the ventilation rates in the building, and it's going to depend on how many different entry points are in the building. So on the next slide, we're going to explore that a little bit further. So on the next slide, on this slide here, and how radon gets into your home, I want to bring to your attention a couple of things. So radon can come through or be pulled into a home through construction joints, where the cold joint between the concrete floor and a wall, particularly in a basement, forms. Radon can come in through cracks, the smallest of cracks in concrete walls and floors. Radon can come in through your sump pit if you have one, through the drain tile system into the sump and then into the home. Cracks through solid floors, through hollow block walls. Radon could come in through gaps around service pipes and utility lines that penetrate the walls and floors of a structure. Radon can move through suspended floors. And last and certainly not least is radon can move into a building through the use of water, through the use of groundwater, just through normal household use. About 85 to 95% of radon gas in a building or in a home comes from the soil, and through those soil opening examples that I gave. But there are other ways that radon can be introduced into a building. One way is through emanation from building construction materials. Anything that's constructed from earth materials has a potential to have some uranium in it. That's usually about roughly 2 to 5% of the time of the source of radon in a structure. There's the diffusion through concrete. Concrete, though it looks solid, is indeed porous, and if the source of uranium and radium under that concrete is strong enough, it could actually work its way through the concrete. That's still a small amount. It's still only 1 to 4%. Water supply is less than 1%. That being, it takes roughly 10,000 picocuries per liter of radon in water to increase the indoor air radon concentration by 1 picocurie through normal household use. So anytime you're dealing with radon indoors as an issue, the primary source of that radon is going to be from the soil gas. It's going to be 85 to 90% of the time it's coming from the soil. The important takeaway here is that radon gases, decay products, do come directly from the soil. So I bet you're all wondering how radon gas moves into the house, right? How does it get into your house? Well, in the next slide, Eileen, we're going to explore how negative building pressures and radon help radon move into a structure. So there's 3 primary ways. We have buildings. Buildings, our homes, and all buildings that are in contact with the soil are under some type of vacuum or negative air pressure. That negative pressure or little vacuums actually help to draw soil gases from the soil below the home or wrapped around the soil into the building. The building vacuum is created by 3 different methods, and actually a combination thereof. That's the weather outside, the stack effect in the building, and the mechanical exhaust systems. With regards to weather, we're talking about wind blowing across the top of the house. Wind effects and strong winds can blow over the top of a building, including a house, pulling air into and out of the building. Also, temperatures and barometric pressures or air pressure changes and precipitation can influence radon levels in a home. The amount of snow on the ground, the amount of frost in the soil outside the structure, the amount of water in the soil through heavy rainfall can actually have an impact on how much radon is in the home, because those situations, those types of precipitation capping the soil outside the home, radon's coming out and it's going to find a way in through other ways into other openings. The stack effect in a home. That's the result of heating the home and warm air rising through the home. Which stack effects are pretty strong this time of the year when we're heating our homes to 60, 70 degrees on the inside and the air temperature outside is 30, 40, or even lower than that outside. So you're creating a stack effect with rising air moving out of the house. And by doing so, you're creating negative air pressure because the air has to make up somewhere. It's going to come from the bottom of the structure, from the soil area, helping to tug radon and any soil gases into the building through stack effect. And then lastly, the combination and use of combustion or ventilation equipment. That's what we normally use, or our exhaust fans in our homes. The kitchen fans, the bath vents, those types of things help to put our homes under a negative pressure. So on the next slide, it's important to note that it doesn't matter where you live, as we heard in our public service announcement. All homes in a neighborhood should be tested. Shouldn't rely on the testing or the visible presence of a radon system on a home. And the reason for that is that we get those sources of radon and uranium and radium in the soil can vary from place to place. Is not consistent from beneath one structure to another. Each home, even though they were recently built, if they were built in the same subdivision, still behave differently. Some homes with lots of uranium in the soil may have a higher chance of elevated radon, but some homes in the same area will have low levels of radon. And the flip side of that is you could have homes in low areas of radon, low areas of uranium in the soil, but still have high radon in the homes. That's why it's important just to test a home so you know exactly what's happening. Excuse me. Radon levels in a building do fluctuate from morning to night, from day to day, week to week, and seasonally. This time of the year, we encourage residents who are doing radon testing when they do a short-term test, and we're going to talk about that here in the coming slides, about the importance of testing over multiple seasons because of those fluctuations and changes in weather conditions. Those can all have an impact on a home. Here, as I mentioned previously, that all homes in all 83 counties, we have homes that have tested high for radon, regardless of soil types beneath their homes, or regardless of the soil beneath their homes. And it's important that all homes be tested. So thanks for the next slide there. So now we're going to talk about what about my house? How do I test? So next slide, Eileen. So you cannot predict radon levels based on the type of heating system that you have, the foundation type, the age of the structure. You can't really go by that. Radon is not a old home issue. Radon gas is any home issue or any building issue because of our close contact with the soil. Radon is odorless, colors, tasteless, as we mentioned before. There are no physical signs to alert you of its presence in the home. It doesn't have a smell. It doesn't discolor the foundation. There's no visible traces of gas, etc. There's no warning signs. Radon is not going to cause you a headache. It's not going to cause fatigue or skin rashes or anything outwardly that something is going on. The only way to know whether the home has a problem is to test the home. Even if the home tests below the US EPA action level of 4 picocuries per liter, a radon test should be conducted every 2 to 5 years. So how do you test? Next slide. There are multiple ways to test a home. Here at the Radon office, we purchase radon short-term radon test kits using our state indoor radon grant to purchase test kits, and we distribute them through our statewide partners, many of which are our local health departments and city health departments in the state. We have tribal partners as well that partner up with us, as well as other partners who around the state. Our Healthy Homes programs in West Michigan, for example, also partner with us. So, but primarily test kits are distributed through the county health departments or city health departments around the state. Other avenues for purchasing a test kit for doing a radon test is through your county hardware store. Many of the radon laboratories have their online stores for direct purchasing of radon test kits to just to the end user. And lastly, a professional tester can be used can be hired to do the radon testing if you're not comfortable with do-it-yourself. The do-it-yourself radon test kits are very easy to use, and it's just recommended that you follow the instructions that come with those test kits. Next slide. The other option is additional testing options are longer term testing. Those previous slide we talked about short term. And this slide we're talking about longer term tests. There are alpha track tests that could be used for 90 days to a year long. There's the continuous radon monitor that is often used by radon professionals to test a home. Those are very good as long as the use and instructions have been followed. There are consumer grade level, what I call consumer grade digital devices on the market that are commonly being used these days. These devices are great for getting information if you're trying to determine if you should do testing. We don't have a formal recommendation for those. Those devices are not formally certified by the Environmental Protection Agency or elsewhere, or any of the national radon laboratories. However, those devices are very good at helping people to make a decision to take action, particularly if they're seeing that the device is saying that they have radon levels over the action level. It's good that those devices are helping people take action. If you have a device and you're concerned about radon levels, it's always recommended that you follow up with a charcoal test kit like we just showed on the previous slide, and do another test and confirm what you're seeing on the digital device. If your charcoal test is showing radon levels above the action level of 4 picocuries per liter, then you want to take additional steps to reduce the radon levels in your home. In the instance of a radon or a real estate transaction, a radon professional should be used to obtain a radon measurement. This should not be left to the seller or buyer to do a do-it-yourself test. It really should be done with a radon, a certified professional to take those measurements. Next slide. Typical radon levels. This is just some information. You can have radon levels between 20 and 100,000 picocuries in the soil. Most soils range between 20 and 2,000 picocuries per liter. The average outdoor concentration for radon is just under a half a picocurie per liter. Radon in air indoors can range anywhere between 1 to 1,000 or 3,000 or more picocuries per liter. In the United States, the average indoor radon concentration is 1.3. And again, as I've mentioned a few times, is that the EPA's action level is 4 picocuries per liter. One thing to note here is, yes, I've provided some ranges of what radon in soil may range. It's important to note that testing the soil prior to building a home will not necessarily predict what the radon levels will be in that structure. Yes, you're going to find radon in the soil because it's part of the environment, but the only way to know how the how much radon is actually going to move from that soil into the home is to wait until the home is actually completely built, and then test the home with all the windows and doors closed on there. But hopefully, if you're building a home, you're going to build radon resistant new construction, which I'll talk about on a few slides. Next slide. Common testing durations is for short term is 2 to 7 days, just some background, and for long term test is 90 days to a year. Again, you need to take action if the radon levels are greater than or equal to or greater than 4 picocuries per liter. Some ideas about testing, just some notes about when you're placing a radon test in a home, it's best to test the lowest livable area of the home, so preferably the basement, because that's closest to the soil. It's wrapped around the soil, it's in the soil. In the absence of having a basement, if there's no basement and it's a slab on grade or it's a crawl space underneath the home, then test a living space above that crawl space, or in any of the rooms on the first floor. Best rooms to test would be bedrooms, living rooms are the better place to test. Bathrooms, kitchens, closets, those are not livable spaces and should not be used for testing. Testing a crawl space is not an appropriate test either, because that's generally not a living space. And yes, you're going to probably find radon in it because if it's got soil in it and not encapsulate it, but that's not what you're trying to find out. You're trying to find out what the radon levels are in the living space. So to test the spaces adjacent to that crawl space, or definitely the rooms above it. Just a word of caution about testing during storm events. As I mentioned in previous slides about those wind changes and changes in air pressure, rapidly changing air pressure can adversely affect the radon test results. So you want to keep in mind when you get ready to do a test, take a look and see what the weather conditions are forecast in the days ahead of your planned radon test. Next slide. Okay, so now we're going to move after we've done the test, we've got our test results back. You're thinking, what do you do? So there's some things to keep in mind. If the radon levels are above the action level of 4 picocuries, and you can confirm that with additional testing, a radon mitigation system may be the best way to go. Radon mitigation systems are any system or process used to reduce radon concentrations in the building. Again, I mentioned the ways that our homes are placed under vacuums. The radon mitigation system is designed to overcome that vacuum of the home by using a fan and piping to pull radon from underneath the structure and discharge it outdoors. A radon mitigation system is very effective at reducing radon levels regardless of the initial testing levels. So it doesn't matter if it was 4 picocuries or 400 picocuries, a properly installed system will reduce the radon levels to under the action level. Next slide. So on the screen, it's just some examples of what a radon mitigation system may look like on what I would call a retrofit. These are active radon mitigation systems, active meaning that they actually have a fan. So on the left, which is an interior design, we have a radon mitigation system that's starting in the basement and routed through the home, routed into the attic. The fan is placed on the piping in the attic, and then the exhaust pipe is protruded through the roof. That is a way a radon mitigation system could be installed in a home. On the right is the exterior design, which most people probably see and not know that that's what they're looking at when they drive by it or see it on their neighbor's home. And that is the radon mitigation system with the piping starting in the basement, and then the rest of the system is routed outdoors, including the fan, the additional piping up to the roof line, which is most visible. For some, that's aesthetically not pleasing to them. And so there's things to do to work around that, including painting. Painting them is actually an option to make them blend in to the structure. But however it's installed, as long as it's installed properly, radon fans should be in an unconditioned living space. It should be outside of the home, or they should be in a location that's above the conditioned space and not below where people are living or sleeping. The radon fan should never be installed in the basement for that matter. So we just want to put those out there as a reminder when you're looking at a system that these fans should definitely be outdoors or in an attic location. The indoor radon program, where I'm the specialist, recommends the use of a certified contractor to install a radon mitigation contractor. And when looking for a contractor, you want someone that will follow the national standards for installing a radon mitigation system. Homes with radon mitigation systems should be retested every 2 years. There are performance monitors on the radon mitigation system. Those include a U2 manometer, which has fluid in it. Usually when you see those, they're usually a little bit offset. Usually looks like a little bit of a J color when you're looking at a J shape in color on the YouTube. As long as that J shape is there in the YouTube of fluid, there it means air is actually moving throughout the system. What it does not do is tell you what the radon levels are in your home. And that is actually a common mistake that is made is that the belief that the U2 manometer is documenting the radon levels. It actually is only measuring the air pressure in the pipe. The only way to know the radon levels in the home is to test. And again, testing with the radon system should be done every 2 years following installation. And then finally, homes can be built radon resistant from the ground up to reduce the incidence of radon entering the home. These systems are very effective. These involve a system of additional gravel built underneath the floor of the home before it's built, adding a vertical riser pipe that runs from the gravel bed vertically through the home to extend above the roof line, sealing and caulking all penetrations through the concrete, sealing the concrete floor where the floor and the walls meet, and adding an additional outlet in the attic next to the pipe. And the reason for that is if the home later is tested and the radon levels exceed the action level, the pipe can be cut and a radon fan can be put in to make it an active fan, an active radon system. But the premise with the passive venting in a radon resistant new constructed home is that the home's the warmth of the home will heat or warm the pipe for the radon system, and there should be a natural convection of rising air within the pipe to pull and encourage the radon underneath the home to move through the pipe and then out the stack. So there are ways to make a home radon resistant. It's not radon zero because again, all homes are in contact with the soil and there's always radon present. Next slide. So I have included on the screen here some resources that are available on our website. That's at michigan.gov/radon. Took a snapshot here, so you'll see there's information for students and teachers. There's a Radioactivity book, a coloring book for our younger students. There's information for the US EPA radon information for kids, students, and teachers. This information at the National Radon Program Education Resources provides access for radon science fair project ideas for junior high and high school, and it provides contacts for a national radon poster contest, which I want to put a plug in. I really hope to see Michigan get in on this national poster contest. What the premise of this is that each state has their own poster contest. They select winners. The state's winner of their state's poster contest is forwarded on to the national poster contest to compete against the other states. And then the national poster contest winner is selected and announced during Radon Action Month each year. So I'm really hoping that Michigan can join in on that. And I'm hoping that for our teachers that are on, or we will be watching this later, we'll be interested in doing that. The EPA RadTown also is another great resource for teachers and students, providing information about radiation education. The site contains fact sheets that explain the different types and sources of and uses of radioactive materials and radiation, and it includes RadTown classroom materials for teachers. And with that, I am done with the section on radon. I hope everyone is going to test their homes if they haven't done so. Thanks.
Thank you so much, Les. That was really good information. Um, just to make some quick connections before I open it up for questions for our last few minutes, the team has done a wonderful job of sharing throughout really interesting resources that you could pull into your classroom. And I want to just call out a couple of things that were mentioned. I will share all of those resources. All of the links from the presentation will come to you along with the recording in the next few days to a week or so. But to find all of the things that Les was just talking about, michigan.gov/radon, that's our primary page there. We do have the EGLE Career Series where we highlight staff from within our department who do all different kinds of jobs. So if that career connection is a piece that's interesting to you and your students, definitely check that out. I'll link it in the resources. We actually don't have anybody yet from this particular section of EGLE highlighted in the career series, and we would really love to. So hopefully you'll see one of them in the next little while. But we do have, someone similar along the lines who does air sampling of groundwater or of ground soil samples, which is really interesting, and that's kind of a related field there. And then I really do want to echo Les's support of EPA's RadTown resources. They are so cool, and they've updated them in the past couple of years to make them just really appealing, visually appealing, interactive, interesting for students. So a couple of those pieces are screenshotted on the slide here. So there's materials that you can use to teach your students about those different types of radiation, the different particles, like we talked about earlier. There's some cool pieces about women in radiation history. I was just thinking about this. There's a book I just checked out from the library. I haven't read it yet, about radium girls. So there's some cool history that you can pull in and career pieces. I just really encourage you to check it out, and I will share all that information with you as we get the recording to you in the next couple days. Oh, another screenshot of some cool pieces from RadTown. You can look at sources of radiation, not just radon, but other sources of radiation that you might find outside or in your community. And if you feel like I signed on to watch this webinar about radiation and all I heard about was radon, it's because the radon is your primary source of radioactive materials in your life, most likely. Unless you have some kind of unique job situation. So it's very, very important, very critical that you manage your exposure to that. I'm going to open it to questions in just a moment. I'm going to stop the recording and give you a chance to unmute to ask questions that you might have, but I want to put a plug in for the last 4 EnviroSchool series sessions of the year. We're going to go through May, and then we'll take a break for the summer before coming back next year. So we have in February, we have coming up some focus on climate and energy and how Michigan is trying to achieve our climate neutrality or our carbon neutrality goals. We have a session on spatial analysis using mapping and geographic information systems to ask and answer questions, and specifically using EGLE's data sources. I just finalized the title of the compost one, but didn't get it into the slide in time. But we have a session focusing on food waste, composting, and what you can do to implement those programs in your schools in April. And then we have an air quality monitoring program with one of our toxicologists coming up in May. So definitely check it out, share it with your friends. All this information is on the EnviroSchool webpage, which you probably got to register for this, and I will share out at the end as well. So with that, we're going to have a little bit of discussion. I'm going to quick pop up on the screen my contact information and our general contact information in case you need any of that. Feel free to reach out at any time, and all of these resources will be sent to everybody who was registered for this webinar. So even if you couldn't make it today, those folks will get the resources emailed to them as well. So now I'm going to stop the recording, and then I'm going to open it up for questions.